So this video is going to explain how to solve the problems on sheet 2. So first of all, we've told that we've got the curve y equals x sine 2x, x in radians, and then this bit of text here just explains something that we can easily see from the diagram. So for part 1, find dy by dx. So y is equal to x sine 2x, and we're expecting on core 3 to see the chain rule or the product rule or the quotient rule, and this is a product, it's the multiplication of the x function with the sine 2x function. So we apply the product rule. U is equal to x, which means that du by dx is equal to 1. V is equal to sine 2x, which means that dv by dx is equal to 2 cos 2x. And if we weren't confident, we could use the chain rule to differentiate that and get that, but this is the sort of form you should be able to do by inspection. And now we substitute, so dy by dx is equal to u dv by dx plus v du by dx, and it's just a simple substitution. So dy by dx is equal to, so u, so x multiplied by 2 cos 2x plus v, which is sine 2x, multiplied by 1. So that is our answer to the first part. Hence, show that the x coordinates of the turning points of the curve satisfy this equation. Okay, so we don't need to get freaked out by this. We've got turning points of the curve, so obviously turning points are found. So turning points that's when dy by dx equals 0. Okay, so we set this to 0. So we have 2x cos 2x plus sine 2x is equal to 0. And hopefully this can be turned into this. And as you can see, we've got the right number of terms. There's 2 terms and a 0. The tan is obviously going to come from doing some sort of divide through, and in fact you can see that to get tan you need sine over cos, so we're going to divide both sides by cos 2x, and that will give us 2x here plus sine 2x over cos 2x, and 0 divided by, this is still 0, and of course that's tan 2x, so we can write tan 2x plus 2x equals 0, QED, it has been demonstrated. And there we go. Now on to the second part of the question. Find, in terms of pi, the x coordinate of the point P. Show that the tangent PQ has this equation and find the exact coordinates of Q. So there are a lot of marks in here, so I'm just going to give myself a bit more room. Okay, let's go for it. So, in terms of by the x coordinate of P, so at P, y equals 0. I'll just go back up to the graph to explain how I know that. So at P, y is equal to 0, that's because it's on the x-axis. And of course we're trying to find the x-coordinate. So we know that y equals x sine 2x, which means that x sine 2x equals 0. And that rearranges the 2 solutions, so either x equals 0 or sine 2x equals 0. And this is, of course, just a simple sine graph. And if for sine x2 equals 0, then obviously sine could be 0, or 2x could equal pi, because we're working in radians. It's supposed to be an x, which means that x could equal pi by 2. And that is our answer to the first bit. So the x coordinate at p. Okay. Not particularly clear, that one maybe, but hopefully you should be able to follow that. Now, show the tangent PQ has this equation. So, tangent PQ. So first of all we need the gradient. So at P, the gradient is equal to 2 times pi over 2 cos 2 pi over 2 plus sine 2 pi over 2. And all I've done there is I've substituted the x coordinate at P, which I've worked out, into my expression for dy by dx, which is in the last part, so just there. And that's giving me the gradient at point P, and this turns out quite nicely. So what we've got here, so we've got the sine of pi, which of course that bit there is equal to 0, and here we've got the cos of pi, which is minus 1, and here we've got 2 pi over 2, which of course is pi, and so the whole thing ends up as being minus pi. That is the gradient. So we've got the gradient, so we just need to stick it all in y equals mx plus c now. So we've got y is equal to minus pi times x plus c, and then we're going to substitute our point P, which of course is pi by 2, 0. We worked that out before, and that gives us 0 is equal to minus pi times pi by 2 plus c, and that means we've got minus pi squared over 2 plus c, therefore c equals pi squared over 2, and that means that we have y equals minus pi x plus pi by 2, pi squared by 2, and of course we want to show that it turns out to be this expression here, so we need to rearrange it a little bit, which is straightforward. Multiply through by 2, so we get 2y is equal to minus pi x plus pi squared over 2, and then we multiply through. Have I multiplied by 3? I did, yes, so it should be 2 there, shouldn't it? Scratch that one. Unfortunately, the eraser on this is not working at the moment. So we multiply through by 2, so we've got 2y is equal to minus 2 pi x plus pi squared, and then we just subtract this, add this over here, so we've got 2 pi x plus 2y is equal to pi squared, and that's what we've been asked to show. Then the very last part of it, find the exact coordinates of Q, and remember the word exact, that means there's not going to be any decimals, it's going to be have pi's left in it in this case. So when x equals 0, then y is equal to minus pi times 0 plus pi squared over 2, which of course is pi squared over 2, so point Q is at 0, pi squared over 2, and just to link that back to the graph, remember Q is in fact the other end of that tangent, so that's Q there. So I substituted x equals 0 because it's on the y-axis, so x equals 0, and I worked out the y-coordinate. Okay, last bit now. So, given that x equals cot y, show that dy by dx is equal to this expression here. So, off we go. So we know that x is equal to cot y, and that means that it's cos y over sine y. And of course this is a quotient rule problem here, so we can say that v is equal to sine y, which means that dv by dy is cos y, and u is cos y, which means that du by dy is minus sine y, and it's also useful if you're going to use a quotient rule to work out v squared, which in this case is sine squared y. So there's all our bits, and now substitute into the quotient rule. So this of course is dx by dy. Notice it's not dy by dx because this is all the wrong way around. And v du by dy minus u dv by dy all over v squared. And you've got to make sure you get this right, really important. So dx by dy is equal to sine y times minus sine y minus cos y times cos y all over sine squared y. And this simplifies down to minus sine squared y minus cos squared y all over sine squared y. Now, tempting to do several things here, but the one that's going to get us what we want is to split this up. So we've got minus sine squared y over sine squared y, and then we've got minus cos squared y over sine squared y, and that gives us minus 1 from this term here, and then minus cot squared y from this term here. And we know from the start that x is cot y, that means cot squared y is x squared, so that means we've got minus 1 minus x squared, and that's dx by dy, so dy by dx is 1 over that lot. And we can take the minus out, and an equivalent expression is this, which of course is what we're trying to show. And there we go. If you've got any questions, email me.